So as people are getting on and joining us and we're waiting for all the participants to log in, there is a poll launched. It's optional if you want to participate. It's about the landscape of ADAMTS TS13 testing. So please feel free to jump in and answer any of those questions, and we will talk about those results at the end, after the slides. Yep, so the attendees are still climbing, but as they are, I will go ahead and get started. And thank you everyone for joining, and welcome to today's webinar entitled Breaking Barriers, the Evolution of ADAMTS TS13 Testing, sponsored by Diapharma. So Diapharma is a specialty distributor focused on hemostasis testing for diagnostic and research uses. We're proud to work with our Austrian partners, Techniclone, to provide the Technozyme ADAMTS TS13 activity ELISA, which was newly authorized by the FDA for in vitro diagnostic use, which is really exciting. Techniclone has had coagulation on their mind for 35 years and aims to provide global customers with superior quality IVD testing in hemostasis. Today's webinar will be given by Dr. Gary Moore and will cover information about TTP, TMAs, and the value add of laboratory testing for ADAMTS TS13 activity. He plans to discuss the significance of ADAMTS TS13 testing, the history and evolution of testing. I am your host or moderator today. My name is Olivia Stricker. I work for Diapharma Group, and I will be joined by Elizabeth Myhall, who serves as Diapharma's ADAMTS TS13 product manager in the US, and also Dr. Nicholas Binder, who is the CSO, the Chief Scientific Officer at Techniclone. They will join Dr. Moore after the presentation for a Q&A session. So please feel free to put any of your questions as the slides progress in the Q&A tab at the very bottom menu on this Zoom platform. Before I hand it over to Dr. Moore, I mentioned at the beginning that I launched a poll that we will review when the slides have ended. Participation is completely optional, but it's really interesting to kind of get a snapshot of what ADAMTS TS13 testing in the US looks like right now. So without further ado, I would love to hand it over to Dr. Gary Moore. He is an academic and clinical expert in hemostasis and thrombosis. He has many, many years of experience and direct experience with ADAMTS TS13 testing and TMA diagnostics. He is an active member of ISTH and SSC subcommittees, and he's now serving as the Director of Clinical Diagnostics and Research at Techniclone. So, Dr. Moore, feel free to take over.
Okay, thank you very much. Okay, so first of all, I'd just like to thank Diapharma for inviting me to give this presentation on ADAMTS 13. Thank you very much indeed. So let's kick off. So let's first have a look at ADAMTS 13 in its day job. Ultra-large von Willebrand factor is initially secreted from the viable Pallady bodies in the endothelium, and a proportion of that ultra-large VWF will become transiently bound to the endothelial surface. And you can see from that photon micrograph, those green blobs are these massive von Willebrand factor filaments. Von Willebrand factor is one of the largest molecules in the body, larger than some virus particles. And because it's bound to the endothelium, it will unfold because of shear forces and expose the A2 domain to allow ADAMTS 13 to cleave the von Willebrand factor so that smaller von Willebrand factor multimers are released into the circulation, whereupon they undertake a globular formation. Now, once that globular ultra-large von Willebrand factor reaches the microvasculature, it will unfold and can be further cleaved by ADAMTS13. We have far fewer thrombogenic multimers, and it will generate smaller multimers, which will not spontaneously interact with platelets to form clots. But of course, the reverse is true in thrombotic thrombocytopenic purpura, which can be either a congenital or acquired deficiency of ADAMTS13. And this deficiency leads to an accumulation of these hyperfunctional ultra-large multimers in the circulation, whereby we see indiscriminate attachment of von Willebrand factor to platelets, spontaneous formation of von Willebrand factor-rich clots in the small vessels, which ultimately leads to end-organ ischemia, a consumptive thrombocytopenia, and ultimately a mechanical hemolytic anemia as the red cells try to travel through these multiple small blood clots, and the red cells become sheared as they try to pass through. Let's have a quick look at the brief history of the recognition of TTP. Not quite 100 years ago, in 1925, it was first described by Mosevich in a 16-year-old girl. And it was nearly over 20 years later, that a review of 12 cases actually recognized TTP as a separate disease entity. And they wanted to call it generalized arteriolar and capillary platelet thrombosis, all 19 syllables of it, which they thought was too long and cumbersome. So they decided on thrombotic thrombocytopenic purpura, which with its only 12 syllables is apparently a bit easier to say. In 1960, Shulman and colleagues reported on an 8-year-old girl whose symptoms had begun at a year of age. And in 1966, a review of by then over 200 cases formed the classical pentad of the clinical presentations of thrombocytopenia, microangiopathic hemolytic anemia, neurological symptoms, renal insufficiency, and fever. Later on in 1978, Upshaw reported on an older female who had recurrent episodes since she was only 6 months old, and he noted the similarities with the case reported by Shulman. So a year later, Upshaw named it the Upshaw-Shulman syndrome, making sure his name went first. And in 1982, it was revealed that in both types of TTP, there are circulating ultra-large von Willebrand multimers when the patients are in remission. It wasn't until 1996 that 2 groups independently identified the von Willebrand factor cleaving protease enzyme, and both papers were published one after the other in the same issue of Blood. A year later, it was shown that this is the enzyme that is deficient in congenital TTP. And a year later, another 2 groups, again publishing one after the other, this time in the same issue of the New England Journal of Medicine, showed that it was IgG antibodies to this protease that caused acquired TTP. So it is Upshaw-Shulman syndrome that we use to describe congenital TTP. It's very rare, autosomal recessive, and makes up no more than 5% of all cases, usually developing early in life. And the mutations will affect either the synthesis, intracellular trafficking, secretion, and/or the actual proteolytic activity of the enzyme. So that means most TTP, acquired TTP, is autoimmune in nature, almost always due to IgG antibodies, which can either be a primary immune-mediated disorder or secondary to other autoimmune disorders, or as you can see in the list, other disorders. TTP is, of course, a thrombotic microangiopathy, but it's not the only one. So we need to perform a differential diagnosis to distinguish it from the others, such as the Shiga toxin-like producing hemolytic uremic syndrome, the atypical hemolytic uremic syndrome, which can be either due to hereditary defects in complement regulation or secondary to other disorders, or secondary TMAs themselves. So we first need to find evidence of a MAHA, which will come from anemia. Hemoglobin is typically less than 100 grams per litre. schistocytes on the blood film, elevated lactate dehydrogenase and indirect bilirubin, and reduced or even undetectable haptoglobin, and a thrombocytopenia, which is either less than the reference range or at least a greater than 25% decrease from the patient's baseline. Slightly different in pregnancy because it's not uncommon to see a reduced platelet count in pregnancy anyway. So we have a platelet count cutoff of 100 times 10 to the 9 per litre. Combine this evidence with evidence of end organ damage, commonly in the gastrointestinal tract, renal impairment or neurological symptoms, but sometimes other organs such as the heart. And it is at this point that we would evaluate for ADAMTS13 activity and Shiga toxin. But equally, even at this point, if the platelet count is greater than 30, the serum creatinine suggests mild or no renal insufficiency. And if you have initiated plasma exchange, lack of a complete response, then you already know that TTP is highly unlikely. But a positive Shiga toxin result gives you an ST-HUS diagnosis. ADAMTS13 greater than 10% makes atypical HUS more likely, and a result less than 10% ADAMTS13 activity is almost, but not entirely pathonomic for TTP. In terms of diagnosing TTP, the classical pentad these days is in fact largely obsolete. Less than 10% of patients will present with all 5 symptoms, but almost always they will have a thrombocytopenia with a platelet count less than 30 and evidence of a MAHA. Diagnosis of TTP should be considered as a medical emergency. The initial diagnosis is made on the clinical history, clinical examination, and our routine laboratory procedures such as the hemoglobin, the blood film, the creatinine level, etc. If you don't have ADAMTS13 testing available locally, or it's not even immediately available, predictive scores are used, such as the plasmic score or the French score. There is also a Bentley score that uses parameters like platelets, reticulocytes, bilirubin, and D-dimer, but that one never really caught on because it's considered probably too complex. But we should be aware that in patients who are older than 60, that even these predictive scores have a lower sensitivity. They're less reliable in identifying TTP in older patients. Now, just over 10 years ago, one of the first guidelines on diagnosis and management of TTP was published by the British Society of Haematology in 2012, where you can see they specifically said pre-treatment samples should be obtained to measure ADAMTS13 activity levels and detect the antibodies, because at that point, rapid assays weren't available. And they note the diagnosis of congenital TTP would be confirmed by doing one of these assays with a result note of less than 5%, not the more commonly used 10%, and the absence of antibodies. In terms of the use of assays, those early assays, they were too complex, too time-consuming, and had low reproducibility and did not lend themselves to stat testing. They were generally only available in reference centres, and even then maybe only once a week. You couldn't do them urgently. So initial diagnosis had to be based on clinical findings and those basic laboratory parameters. But just over 10 years ago, more rapid assays started to become available, and we started to see publications from laboratories that were adding them to their routine repertoires. And you can see that they were able to report results within 1 or 2 days, or even in some cases within a few hours of the laboratory receiving the sample. And a common conclusions from all of these studies was that these rapid assays based on FRET or ELISA gave more rapid differentiation between the TMAs, more efficient use of plasma exchange without any increase in mortality, and improved patient outcomes, because anybody given plasma exchange that didn't need it, it could be ceased a lot earlier. So there was also a reduction in the financial costs as well. More recent guidelines from the ISTH on diagnosis of TTP, published in 2020, were able to make recommendations based on the availability of these more rapid assays. And we have a recommendation here, recommendation 1, in settings with timely access to activity testing and for patients with high clinical suspicion. If you look down at step 4, based on the result of the ADAMTS13 activity assay being greater than or less than 10%, decisions are made on whether to use or not use caplacizumab. So the assays are directly affecting patient management. Similarly, in recommendation 2, where the assays are readily available, but there is an intermediate or low clinical suspicion, the recommendation is that you wait until you have the assay result before you decide whether to use caplacizumab or not. Caplacizumab is a monoclonal antibody that interferes with von Willebrand factor binding to platelets. There's also a recommendation 3 that without the assays, you shouldn't be using caplacizumab at all. What I'd like to do is draw your attention to some detail in figure 1 and figure 2, including a couple of typographical errors, where the ISTH has introduced a very valuable borderline suggestion. So a result of less than 10, then you make your decision about caplacizumab. But if you have a borderline result between 10 and 20 ADAMTS13 activity, you need to use clinical judgment to guide the treatment. And that should cause you to consider other diagnoses, but not necessarily exclude TTP. And this is because the assays vary a little bit. There's always a certain amount of imprecision and measurement uncertainty. And of course, the timing of the clinical presentation. The patient might present, but their ADAMTS13 hasn't quite gone below the cutoff yet. And you can see in these papers that I quote below that using the cutoff of either 5 or 10%, you don't have 100% or sensitivity for TTP. And some patients who have ADAMTS13 a little bit above that cutoff do turn out to have TTP. So this is a very valuable recommendation. More recently, only last year, the British guidelines have been updated, and they have this to say about the assays. The assays are essential in confirming the diagnosis of TTP. Activity of less than 10, notice the original BSH guideline had less than 5, plus or minus the presence of antibodies confirm the diagnosis of TTP. And again, they reaffirm that the diagnosis or the cutoff of less than 10% has a high sensitivity, but not full 100% for distinguishing TTP from other TMAs. So they repeat the recommendation that pre-treatment samples should be obtained to measure activity and antibody levels. And this early measurement of the activity is recommended over use of the scoring systems. And the assays that they recommend and they talk about are ELISA, FRET, and the more recently available chemiluminescence assays. So let's have a look at those assays in a little more detail. The FRET assay, this uses a von Willebrand factor peptide made of 73 amino acids that contains a donor fluorophore and a dark quencher that exist on separate sides of the ADAMTS13 cleavage site. The fluorophore, the donor fluorophore, is excited at 340 nanometers, but that excitation and fluorescence or fluorophore is quenched by the close proximity of the acceptor. But then if you add the patient sample and they do have ADAMTS13, it will cleave the ADAMTS13 to uncouple the donor and the acceptor, which prevents quenching of energy transfer, and we will see emission of fluorescence, the intensity of which is directly proportional to the ADAMTS13 activity. This is normally a manually performed assay. It requires specific equipment in the form of a fluorescence plate reader, but there is a fully automated version available on the Technoclone Sevron S100 coagulation analyzer, so you can do your ADAMTS13 activity assay at the same time as you're doing the prothrombin times and APTTs and factor VIII assays. You can't use EDTA samples because EDTA is an ADAMTS13 inhibitor. Elevated bilirubin and hemoglobin can interfere with the FRET assay and give you false reduction in ADAMTS13 activity levels, whilst the presence of other proteases can give you a false elevation by cleaving the von Willebrand 73 itself. There aren't any FRET assays that are FDA approved, so they are in the USA and Canada for research use only, not for diagnostic use. The ELISA is a fairly standard ELISA. The von Willebrand 73 peptide is tagged with glutathione S transferase so that it can be immobilized on a microtiter plate using anti-GST antibodies. After incubation, the plate is washed and the calibrator samples controls are added, and any ADAMTS13 present will cleave the von Willebrand factor 73 and expose the cleavage site. After incubation and plate washing, a horseradish peroxidase conjugated monoclonal antibody very specifically directed to the cleavage site is added. Further incubation and washing, TMB tetramethylbenzidine is added as a substrate to the HRP, incubated, and then stopped with sulfuric acid. And the color intensity is directly proportional to the ADAMTS13 activity. Again, typically performed manually, but it can be automated, and it doesn't require any special equipment over and above a standard microtite plate reader that most labs have anyway. Again, you can't use EDTA samples, and interference by bilirubin and hemoglobin, etc., is much less because you've got these washing steps that will wash them away. An important point here is that conjugated antibodies are very specific to the ADAMTS13 cleavage site, while the other proteases that might interfere with the FRET assay, they tend to cleave different sites. More recently available is the chemiluminescence assay. Again, it's using von Willebrand 73. There are other peptides available that are slightly longer, but a lot of them use this von Willebrand 73 in the CLI assay. It's also tagged with GST and anchored with a GST antibody, but this time to a magnetic particle. Incubation with the samples allows the ADAMTS13 to cleave the VWF73 to expose the cleavage site. Then we get magnetic separation and washing, after which an isoluminol conjugated monoclonal antibody directed against the cleavage site is added. Then we get more magnetic separation and washing, and chemiluminescence triggers are added, and the light released is measured as relative light units, directly proportional to the ADAMTS13 activity. This is rapid and fully automated, gives you results within 33 minutes, but it does require a very specific analyzer. Again, you can't use EDTA, and it is affected by elevated hemoglobin and bilirubin to the similar levels as the FRET assay, but more interference than you would see in the ELISA, and there is additional potential interference with rheumatoid factor. Again, this assay is not FDA approved, so in the USA and Canada, it's for research use only. Quite a few comparisons of one or two or more of these assays have been published recently. I'm presenting a few here, but there are others. But they all tend to come to the same conclusion that the manual FRET, the automated FRET, the ELISA, and the chemiluminescence are broadly comparable, especially at that 10% threshold. But a number of studies have reported an overall negative bias with the chemiluminescent assay. More recently, published only last year by what used to be the main reference lab in the UK, and in fact using their own reference in-house FRET method, they took the Technoflora automated FRET assay, the Technozim ELISA, and the Hemosil chemiluminescence assay. So they compared all the current assays available, and as you can see from the R values, they compared quite well. And again, the study showed comparable sensitivity for TTP diagnosis for all of the assays at the 10% threshold. Now, out of 88 samples, 42 were tested on all 4 platforms. And again, they noticed this slight negative bias using the chemiluminescence assay with all 88 samples. There was also a slight negative bias with the ELISA when using just the 42 samples that were only tested on all of the assays, but that significance was lost when comparing all of the samples that were tested. And they did note that some CLI results were lower than 10% in patients that did not, although they had TMAs, they were not TTP, showing a slightly lower specificity with the chemiluminescence assay. So the conclusion from this comprehensive study was that sensors using the chemiluminescence assay should test with an alternative, either the FRET or the Technozyme assay, in patients who have either an atypical clinical picture such as sepsis or an unexpectedly low or slow ADAMTS13 recovery. And if we revisit the more recent British guidelines, their recommendation that a low ADAMTS13 level based on a fully automated assay, and by that they mean the chemiluminescence, may require confirmation depending on the index of clinical suspicion for TTP. But again, the CLI assays were still being evaluated at the time. The BSH guideline also mentions a semi-quantitative assay, so I'll just give you a very quick introduction to it. This is a point of care, ostensibly screening test. The reagents are delivered, you can see at the bottom, with reagent dropper bottles into a little cassette, and the sample delivered with either a disposable PET, or you can use thin pipettes. There's a pre-incubation period for the patient's ADAMTS13 to cleave the VWF73, after which you add that mixture to the well, as you can see in the bottom. Then you add a second reagent that has a biotinylated antibody that is tagged to capture the product of ADAMTS13 digestion. Then there's a wash from a dropper bottle, and you add a tagged antibody so that the product is detected with a streptavidin gold conjugate. And then you have a color produced in your wells in both the patient and the control well, and they are read using color charts that have different ADAMTS13 levels ascribed to them. So if you look at figure B, sample 1 in the sample well, it has the color in the well is even more intense than the highest color zone on the reading chart of 0.8 ADAMTS13 activity international units per mil, so we have a normal result. But if you look at reading the sample 2 or with the color chart, there's virtually no color whatsoever. There was no ADAMTS13, and that matches the 0 international units per mil zone, thereby suggesting TTP. A couple of multi-center studies have been published testing this semi-quantitative assay against mainly FRET and ELISA assays. It has good sensitivity, but very importantly for a screening test, it has a very high negative predictive value in both of these studies. So you have a very low probability of missing genuine TTP, which means you can reliably exclude TTP with the screening test, which will reduce the use of empiric plasma exchange or caplacizumab, but results should be confirmed with a quantitative assay. Again, it's not FDA approved, so it's for research use only in the US and Canada. But of course, breaking news in recent months, the Technozyme ADAMTS13 ELISA has been granted FDA approval as an in vitro diagnostic test, and this is the only FDA approved ADAMTS13 activity assay available. The assay is intended to be used in conjunction with other clinical and laboratory findings as an aid in the diagnosis of TTP in both adult and pediatric patients that are being evaluated for TMAs. Now, I've got personal experience of using this assay. We used it when I was working at St. Thomas's Hospital. We automated it on an automated ELISA platform. You can see here that we got very good reproducibility results, comparable to those published by the manufacturer there on the right. We had a very lower limit of quantification, much lower than the 10% cutoff. So it's perfectly good at finding values below 10%. And we compared the results to the reference assay at University College Hospital, which was the reference lab in the UK at the time, and you can see we got a very good p-value. The conclusions of our study that we now had 24-hour local availability of ADAMTS13 activity assays. The results were available within a few hours. Although the genuine TTP patients did have plasma exchange initiated before the result was available, because the results were available so quickly, the treatment wasn't delayed, but there could be early diagnostic refinement. If the patient turned out not to have TTP, there was early withdrawal of the plasma exchange. So these rapid results prevented inappropriate plasma exchange, unnecessary admission to the ICU for non-TTP patients, and reduced costs. There is a guideline from the ICSH about performing the assays. I've got the main recommendations here for you. They recommend FRET or chromogenic assays as frontline assays because they're sensitive and have good precision. If you look in the detail of this guideline, they do mention the chemiluminescence assays, but this guideline was published nearly 4 years ago, when the chemiluminescence assay was only recently available, and there weren't enough data for it to be recommended in this guideline. They mention the rapid point of care assay I've just shown you that could be used as a screening test, and again, at the time there was limited data. Every calibrator should be traceable to the international standard. And when you report the results, ideally in international units per deciliter for antigen and activity assays, your calibrant should be traceable to this standard, but if you don't have them, you can report as a percentage of pooled plasma. You should always run high and low controls, but don't use commercial controls that have been designed for use in a different assay. And any alterations you make to the protocol should be validated. There is acknowledgement here in the guideline that gross icterus interferes with some FRET assays. You can resolve it by using higher dilutions or treatment with an enzyme, but sometimes you might need to use a chromogenic assay. Also, if you have artifactual or in vitro hemolysis, which, as you saw earlier, can interfere with the assay, first thing you do is get a fresh blood sample. If you can't do that, then you need to make a comment on your report. Where the assay results do not match the clinical picture, or congenital TTP is suspected and the results are normal or only mildly reduced, they do suggest that you go back to those very old, very time-consuming collagen binding assays, but again, they're only available in reference centers. If you do get a decreased activity in a new patient, what they say, and again, you can see they're saying a result of less than 20, you should be performing an antibody assay, ideally the ELISA rather than the Bethesda. And if the results do not match the clinical picture, suspect EDTA contamination and get a fresh sample. Wherever possible, you should use the same assay when you're looking at a patient's result over time. Mentioning the antibody assays, you have a choice. Either the ELISA, which will only detect IgG antibodies, and most, if not all, of the antibodies are IgG anyway, or a Bethesda that is based on whichever routine activity assay you have in use. Again, these assays are not FDA approved in the USA and Canada, and they are for research use only. So which inhibitor assay should you use? The pros of the autoantibody ELISA is that it will detect both inhibitory and clearing antibodies, and in TTP they are both clinically significant, and because of this, ELISA is every time the preferred assay. It won't detect IgM, probably not a problem. You must be sure that the assay you're using will detect all IgG subclasses, so whichever assay you use, make sure it's got polyclonal tag antibodies. The assays vary between themselves, so they may not use the same calibration and cutoffs, so they're not necessarily interchangeable. And of course, if you're using a FRET assay, you've got to use different equipment and reagents to those that you're using for the antibody assay, and it's relatively time consuming because it's an ELISA. For the Bethesda, the pros come in the form of that you can use the same equipment and reagents as you use for your activity assay. You're going to heat treat before you do the assay, so it's going to remove IgM antibodies anyway. And we're used to Bethesdas, so we're used to the assay format and the reporting units. But against the Bethesda assay is that it will not detect clearing antibodies. They make up at least 25% of the antibodies in these patients, and some reports suggest they're up to nearly 50%. So the Bethesda is going to miss an awful lot of antibodies, and you're going to get the wrong diagnosis. You really do need to be using the ELISA. Also with the Bethesda, because you're doing lots of dilutions to find the antibody titer, you potentially alter the equilibrium between the antibody and the ADAMTS13, and you may not get an accurate result, and you get variability because of differences in epitope specificity. And again, it's probably even more time consuming than the ELISA. An alternative you have is something that we actually developed at Technoclone, which is the ADAMTS13 inhibitor mix or aim ratio, which is derived just from a ratio, as the name suggests. So you take the ADAMTS13 activity of an equal volume mixture of the test plasma on your normal pool plasma and divide that by the activity of a 50-50 mixture of the normal plasma and ADAMTS13 depleted plasma or buffer, and you generate a ratio. So in place of merely assessing whether a mixing test goes back to normal or not, which we would do, for instance, with an APTT, the aim ratio is a quantitative value which is derived from the mixing test result of your patient as a function of the measured activity of the normal plasma in which it is mixed, and it's interpreted against an objective cutoff, which for the Technofluor FET assay is a ratio of 0.992. Again, it won't detect clearing antibodies, but if you perform this simple mixing test at the same time as you're measuring unmixed plasma for your diagnosis of a reduced ADAMTS13 activity anyway, and this mixing test is positive, you will immediately have a diagnosis of acquired autoimmune TTP. Again, it's not FDA approved, it's for research use only in the USA and Canada, and you can see our initial results there where the mix ratio detected every functional antibody that we tested it with. The ICH guidelines do talk about inhibitor assays. They mention about heat treatment beforehand to inactivate residual ADAMTS13, other proteases, and IgM, then centrifuge to remove any precipitated protein. And when you do a Bethesda-based assay, they recommend an incubation period of 1 hour. Just a very quick mention of the role of ADAMTS13 testing in other disorders. In von Willebrand disease, some type 2A von Willebrand's disease are actually due to increased susceptibility to ADAMTS13 cleavage. And there is a possibility there is a role of ADAMTS13 in the increased clearance of von Willebrand factor that we see in blood group, and why patients with blood group O have lower von Willebrand factor than other people. We saw a lot of attention of ADAMTS13 testing during COVID-19 because there's a lot of endothelial activation in the immunothrombotic mechanism. So we see a massively elevated von Willebrand factor in COVID-19. So we see quite a significant imbalance. There's much more von Willebrand factor compared to ADAMTS13, leading to an elevated von Willebrand ADAMTS13 ratio. And the higher that ratio, the poorer the prognosis of a patient with COVID-19. The ADAMTS13 is reduced due to consumption. It might not even be that low, but it will be low relative to von Willebrand factor. So it's a possibility that this massive elevation of von Willebrand factor is contributing to the thromboses that we see in COVID-19. And only quite recently, ADAMTS13 antibodies have been reported in more severe COVID-19. In critically ill patients and patients with other TMAs, we can see mild to moderate reductions in ADAMTS13 levels, such as in preeclampsia and malignant hypertension and sepsis, and there may be prognostic value in measuring ADAMTS13, and we see reduced ADAMTS13 again associated with worse prognosis in things like atypical HUS, autoimmune disorders, and transplants. Okay, that's my review of ADAMTS13 testing. Thank you for your attention. We'll now go back to the panel so that we can have a Q&A session with any questions that you may have for the panel.
Well, I got the results for the poll. We entered the poll, and the results are in, and I thought it'd be nice to kind of touch on what everyone said. So about half of people on this call participated, and it looks like it's an even split down the middle, that about half of you are sending out and half of you are doing ADAMTS13 testing in-house. Of those doing it in-house, it seems like most of you are doing it more than twice a week. A smaller amount are doing it daily. So, you know, not as frequently as maybe your physicians might like, but more than twice a week. So accessible when done in-house, and then the rest of you are sending it out. And the typical turnaround time that is seen is between 24 and 48 hours. You know, some of them are getting out real fast, but then one unlucky person is seeing it after 5 days. So that's what that looks like. And most of you on this webinar responding to this survey are either laboratorians or pathologists. And there's a few others that I'm not really sure what, maybe, I don't know what you could be doing. But either way, I think that that's really interesting. And the point to hit on for the ADAMTS13 IVD test is that, you know, it's accessible, and maybe more people could bring it in-house.
But it's very nice to see that the turnaround time is very much in line with the recommendations of the ISTH, so that most of the tests are available within 24 to 48 hours. Back in the days, it was ideally within 24 hours to really make the diagnosis as fast and as rapid as possible to continue with the treatment or initiate treatment. So in this case, it's actually very nice to see that the turnaround, whether it's sending out or locally performed, is done in a very good time frame.
So if anyone has any questions related to the slides, please feel free to put them in. I will just kind of touch again on the fact that we have as a panelist, Dr. Nicholas Binder. He is the Chief Scientific Officer at Techniclone. And then also on the line, in addition to Dr. Moore, who just gave us that great presentation, is Elizabeth Myhall. She is with the Diapharma Group and product manager for the Technozyme activity ELISA for ADAMTS13. So we've had a couple questions come in, and I will just go ahead and read these out, and whoever wants to take a stab at it, go for it. So we have a question that says, can you comment on the implications of the new FDA rules with respect to the Sevron FRET test versus the FDA cleared assay?
I mean, so working at Diapharma as a US distributor, the FDA cleared assay is labeled as IVD, so that could be adopted without having to go through the LDT process with the FDA. The Sevron FRET test currently is research use only, so if a lab were going to bring that on board, the LDT rules would apply for that assay. Hopefully that answers your question. And I don't know if Nicholas or Dr. Moore had more to add to that. But
I think from a regulatory perspective, that's exactly what it is. From the methodologies, as I think Gary also pointed out, they correlate quite well or very well together. So both the FRET assay as well as the neo-epitope ELISA, which is now an IVD in the US. But of course, they have their pros and cons, and one of them making it automatic, being able to be automated on a system is of course a benefit of a FRET-based assay. But that's as Elizabeth pointed out, research use only currently only.
Okay. Another question has come in specifically for Dr. Moore. It says, can you comment on the falsely low ADAMTS13 in FRET testing? Notably, we've observed autofluorescence of the patient sample to cause interference, but unsure of what may be causing this, presuming it's a medication of some kind. I have not seen this described. Have you ever encountered this?
I confess personally, I've never seen it. I mean, it does occur, but it is quite rare. I'm sensing Nicholas wants to come in.
I have seen it very frequent. No, we have actually we have just done a study in Paris evaluating the Severon FRET assay, moving the laboratory moving from the manual FRET assay towards the automated FRET, and they actually have seen in their manual setup relatively frequent samples with high autofluorescence. They have, similar as you suggested, that it could be some medication, and they have built up workarounds in using different dilutions on the FRET assay. Interestingly, in the Severon, we have not seen that because the Severon itself can adapt the light intensity and overcome this autofluorescence, just being an LED-based system over the traditional halogen lamp based fluorescence readers. But in the FRET assays, this is in the manual method, that is typically, or I have seen that as well. Of course, the ELISA does not see that because we just wash away everything, which is not ADAMS.
So the same commenter did have a follow-up saying, can this be mitigated by narrowing the wavelength? And I think you've addressed that with the different lamps, or have you not?
Yeah, I think it's whether, I mean, with whether it's the wavelength itself or just by the technology of using high power LEDs like we use on our Severon to really overcome this autofluorescence in the sample.
Okay. We have another question, more just about future plans for IVD approved products, which I don't know if we're allowed to speak to or not, or you're allowed to speak to, but they want to know if the inhibitor kit will be FDA approved as well.
In line of the, I think, and as Gary nicely pointed out already, that is definitely the way forward to do, and the next step to at least make the portfolio in the US as complete as possible, provide an IVD or moving towards an IVD for the inhibitor or the anti-ADAMTS antibody assay as an inhibitor approach. A Bethesda-like approach is possible, but as Gary also pointed out, does not cover all the inhibitors, as we have these clearing antibodies, which will not be addressed by functional inhibitor testing.
Let's see, there's a couple more questions more about the FDA plans and regulations that I'm not sure we can actively address, but I think that maybe follow-up questions with people's very specific answers about LDTs, could be answered maybe in conversations after this. So I wanted to throw in just a question that we get pretty frequently at DF Pharma when people are inquiring about research use. Can any of these assays be adapted for animal studies, whether it's mouse blood or canine samples?
I know that from the US perspective, I know that we have had some users adapt it, for different model animals, marine or canine. It's obviously optimized for use with human samples. I'm not sure if Dr. Moore or Dr. Binder could speak to conservation of these proteins across species. That would probably be the impact of using a different species, but I know it's been used.
I think in theoretically as both or all the ADAMTS assays base their activity measurement on the ability of the plasma-derived atoms to cleave the 73 amino acids peptide or base of the von Willebrand factor. That has to be ensured that this is active. It might not be as active or in the setup, and there could be differences. But at least to my knowledge, it should work it's relatively conserved and should work in most of the species.
As a sort of slight tangent, I have read about experiments injecting anti-human ADAMTS13 antibodies into baboons and mice, and they are completely inhibitory. So suggesting that the ADAMTS13 in other species is very similar to human ADAMTS13. So it's quite likely that if we tested them with our assays, that they would give reliable results.
And then maybe just to wrap up, a logistical question that I feel like we field often for those in the group that is running, 2 times or more or less than in a week. Can the ELISA kit be split up into multiple runs separate?
Yeah, I think that's one of the beauty of the ELISA also, to have to split it up. I think you can do up to so it's 12 strips to run the study and the sample. You need I think 2 strips, so you would be able to run the calibration curve, which of course with the ELISA you have to run every time the controls and the patient sample individually for 4 to 6 individual samples, and that's actually possible. So the calibrators have stability, the reagents are split and have appropriate stability to do that. So that is possible and often used also in laboratories which do not want to batch, or at least not always want to batch, because they want to offer emergency sample turnaround.
That's exactly what we did in that study of mine from 2019 that we published. A lot of it was based on single patients being tested with the Technozyme ELISA assay. So yeah, it was quite common for us to do them one at a time. And the fact that you've got those strips that are separate rather than one single ELISA plate makes it very easy to do.
All right, well, that seems to conclude the questions. I mean, it's an exciting time for ADAMTS13 and the patients that need testing, as there is an IVD option, and we're all thrilled that DF Pharma and Techniclone can be, the people to offer that in the US. And I would like to conclude today by letting everyone know that after you end this, you'll get a post-webinar survey that kind of can let us know who's interested in follow-up conversations, what your plans might be for implementation, or hurdles or support that you might need for implementing this test at your institution if you do not have an option in-house. And what meetings you might be attending this year, because we are very interested in connecting and having face-to-face conversations. So if you could let us know where you're going in 2024, whether it's ISTH in Bangkok or ASH in San Diego, anybody from Dia
We will
Pharma.
be there.
You will be there. Yes. We would love to connect in person.
We would love to. Exactly.
So thank you everyone for attending and your attentions, and thank you panelists, and definitely Dr. Moore, that was really succinct and beautiful. I love historical conversations like that.
You're welcome.
So
Thank you very much, everyone.
thank you.
Thank you.
Thank
Bye.
you. Bye.